All right. So the little practice problems there. We're gonna finish with this concept of friction, and then you'll have several practice ones to do after this, just to get really good at drawing your FBDs. It says intro to friction. Friction is a force that always opposes motion. That means that if a box slides to the right, the force of friction pushes to the left. The amount of frictional force depends on the materials involved. Since all material interactions are different, we use a unitless number to describe the quantity of friction. And I'm not the best with my handwriting sometimes, so that's the Greek letter mu. It looks like a U with an extra little tail on it. And it's called the coefficient of friction, or for short, you can call it mu. And basically, it's a number between 0 and 1. So if a situation had a mu value of 0, that would basically be saying that there's no friction. So it'd be frictionless. And then if the mu value was 1, that would be very high friction. And we'll look at some examples in a second. So what we'll say is the coefficient of friction is basically like a rating of how much friction is between two surfaces. If it has a rating of 0, it's no friction. A rating of 1, it's really a lot of friction. So because you have different surfaces with different mu values between them, you have different forces of friction. So we're going to say force of friction is a force that's created between two surfaces. And to experience friction, you always need at least two surfaces, right? Because if you picture, like, you take your two hands and you slap them together and you rub them past each other, you need to have that second hand to experience the friction, because you need the microscopic bumps from the one hand to interact with the microscopic bumps from the other hand to have a frictional force. And there's actually two different types of friction. Slide right there. So I'm just going to clarify this a little bit. We have two different types of, I should have said two different, there are two types of frictional forces. So let's fix this. The first type, static frictional forces, or the force of static friction. We use an F sub S for that. And just think to yourself, what does the word static mean? And in this case, we're saying static friction. So it's friction that occurs. So we'll say friction between two surfaces that are not moving. Two surfaces that are not moving. So let's think about this. So what I have here is, I'm just sitting at my desk at home. If I were to take my hand and just put it like palm down on top of my desk, and then my forearm is parallel to the ground, if I slowly push my hand forward, just so my hand does not move, so I'm just pushing my hand forward on my desk, I can feel there's a push back from my desk. Well, that's the force of static friction from my desk interacting with my hand. So this is static friction because my hand's not moving, but I'm still experiencing that force. So physicists like to kind of differentiate between friction taking place when objects are at rest versus in motion. So we're going to say Fs is the force of static friction, and there's an equation for that to calculate that. It's just mu sub s times n. So let's say mu sub s is, remember, our coefficient, mu. So that means there's going to be some value between 0 and 1 between those two surfaces that the problem would just have to tell you. And then n, remember, is the normal force. And normal force would be measured in newtons. All right, so that's one type of frictional situation where the objects are not moving. And then you guess the second type with the force of kinetic friction would be F sub k. And then that's friction between surfaces that are moving. So we'll say friction that occurs between moving surfaces. Okay, and then F sub k, the equation is very similar, just going to be mu sub k times the normal force. So you can see these two equations are very similar. The only difference is that if you want F sub s, you have to use mu sub s, and if you want to get your force of kinetic friction, you have to use the mu sub k. And you're like, well, Mr. Hunt, this is super confusing. Where do you get these numbers? Well, material scientists and engineers have measured these different values for the different surfaces. So if you look, let's just look at, picture you get those brand new rubber tennis shoes when you're a kid, with the brand new rubber, and you touch your foot on the concrete. You remember when you first touched the concrete with your rubber shoe, it felt super grippy, right? So the reason why is because the mu value, mu sub s, was 1. So basically when you plant your foot and it does not move, it had a really high coefficient of friction, static friction. Now you can picture too as you were to slide your foot on the surface of the sidewalk, the frictional force actually dropped, and you can see, well, the coefficient of static friction is 1, and that means when your foot's at rest against the sidewalk, the frictional static friction is greater, and then as it slides, the friction actually drops. And you can look at this, if you look down this column here, those are the static values, and these would be if the two surfaces are sliding past one another. And just take a moment to notice, if you compare, say for example, you have a waxed ski touching snow, but they're not moving, it's just touching, versus a waxed ski and snow where it's actually sliding. And just keep comparing the static versus the kinetic, static versus the kinetic for each one of these, and see if you come up with a little observation. The observation that you should notice is that static coefficients are larger than the kinetic coefficients. And typically what that means then is your force of static friction is going to be greater than the force of kinetic. And the best way to picture this is kind of where we'll finish today, is go back to our example where you take your hand and put it palm down on your desk, and then make sure your forearm is parallel to the ground. If you were to push your hand, but don't let it move, you can feel there's a static frictional force pushing back on your hand. But now push your hand so that it just starts to slide a little bit. And you can feel it slides easier than when it was at rest. And the reason why is because the force of static friction that holds your hand in place is greater than the force of kinetic friction that tries to slow it down. So that's why when you're driving, you never really want your tires to be sliding, because then you're kind of out of control, right? Okay, so that's just a quick introduction, and then what you're going to do is just take a moment to try doing some FBD practice. And then what I'll do is I'll post some answers so you can check to see how you did, because we just want to practice getting the accurate FBDs. I'll point out, if they tell you that you have a mu value, like in this problem right here, they say mu sub s is 0.91. That's basically telling you that there's a force of friction in this problem. So they tell you if there's a mu sub s between the block and whatever the surface is, that means that there's a force of friction. And then the next one, notice they explicitly say that this is a frictionless ramp. So just kind of pay attention to that. You're drawing the free body diagrams for these problems, and then you're going to go on to these problems here where you're pulling a big crate. It says of delicious junk food. We're going to switch that to, let's go, still delicious, but let's go health food, just to make sure you're eating healthy, And then on the very last page, you got another example of looking at net force on a skydiver who, it looks like in this thing he's not wearing a parachute, but then rest assured, you can see he's wearing a parachute down there as that skydiver falls. Cool. So thanks for watching. That's the introduction to free body diagrams.